Alright, welcome back. Blueprint 101, Section 3, Unit 2, Engineering Drawings. We're going to talk a little bit about bilateral tolerance examples. Okay, so our first here off the PowerPoint, and again, you don't have to just look at this. The focus and the clarity will be better off the PowerPoint on your Blackboard page as well. Okay, if you could quite possibly open up two, that would be great. The video and this. So we're going to break through this, or start with this top one. Diameter of 500 thousandths plus or minus 2 thousandths. So we've been fairly comfortable working with that. Basically what that's telling us here is the upper and lower limit is exactly what we said. 500 plus 2 thousandths, 500 thousandths minus 2 thousandths. So 502 to 498. Okay. Total tolerance, upper limit to lower limit, we're at 4 thousandths. We know that because it is 2 plus, 2 minus, so 4 total. Now sometimes you're going to find things that have different tolerances. So these are the bilaterals. So here, this next print shows us 500 thousandths diameter, ½ inch, plus 4.004 thousand to a minus -2. Okay, thousandths of an inch. So now we break it down. We got 500, so we're allowed 504 on the top side, on the larger side. But on the bottom side, we're subtracting. We can only subtract 2, so we can only go down to 498. Okay. So we have a greater tolerance of 6, but you notice they're a lot more lenient on the plus side than on the negative side. This is going to matter when you start looking at running fits and so forth, different cylinders, coefficient thermal expansion, things like that. You're going to see tolerances that might have even 0 on the negative side, but you're allowed to be a little bit larger on the bottom side, okay? Or on the opposite side, I apologize. Here on this one is the exact opposite. The plus is 2 thousandths, negative is 4 thousandths. So same thing, a total of 6, but we go to 502 down to 496. Okay. So as you can tell, the addition and subtraction of decimal places is extremely relevant within machining and welding. Machining more than welding. Welding has a tendency to show a lot more fractions instead of very fine precision, but there's a lot of times that we'll have to do both. We may weld it together or repair it and then machine it back down to a certain tolerance as well. Okay? So real quick, next slide. Here's the same thing. Here's an example of the top section is ½ inch plus 4 but minus 0. So it can be 500 to 504 only. Shows you your upper limit, lower limit, plus 0 and -4. Same thing. These are unilateral tolerance examples. So there's only tolerance on one side versus before there was tolerance. Bilaterals show tolerances on both sides. Okay, the plus and the minus. Unilaterals only have one tolerance, either on a positive or a negative, but only one side will allow it. All right, so here's limit tolerance examples. Look through this on the PowerPoint. I'm not going to talk about it too much. We've been talking about it for quite a while. Okay. Here it just gives you references. So as well, we're talking about the top section. It's 0.125 plus or minus, so that's a bilateral tolerance. You can be on both sections. B is showing you 5 thousandths, a plus and minus, so again that is a bilateral tolerance. Now B shows sizes with unspecified tolerances. So here we're at 2.50 inches. Okay. This is where we revert to the title block. It shows that dimension has a tolerance of plus or minus 5 thousandths. So 2.5 is 2.505 or 2.495. Okay. Again, it gives us a bilateral here in the title block. It may not. It may only give you a unilateral, allowing a positive or a negative, not both. Okay. So let's break this down here. So here's where I had this backwards earlier. Okay. Because again, remembering that it takes away material. And I erased it. But before, what I had is I showed the larger number on the top side of 10.4, but that actually 10.4 diameter would take away more material. So this is the least material condition versus the 10.2 leaves more material because it's smaller. So that's the maximum material condition, okay? These are basically, you may see these instead of having a specified number with a print tolerance, this is what it's giving you, 10.4 to 10.2, 6.6 to 6.0, moving in that direction, okay? You can tell even the position of this measurement gives you not just the diameter size, but now this position as well. So this is what we talked about earlier. We went into that feature frame. We had the circle with the crosshair type symbol in there. Okay, so that was the position. So here the position was only 4 thousandths or 0.4. So 400 thousandths difference in position as well. Okay. All right, so classifications of fit. Relationship between sizes of mating parts. The allowance is there's a minimum clearance, maximum interference between parts. Fits, there's running and sliding, which are denoted as RC. Locational, which is LC, LT, LN. And a force fit, an FN, which means that you're going to press it, okay? We're going to go through these as well. Interference between mating parts. The hole is smaller than the shaft, or the hole is larger than the shaft, shaft smaller than the hole, and so forth. Okay. So we're going to look at the book. Talk about classes of fit. In order to do this, sorry, I just unloaded just made the mistake of unplugging the camera. Okay. All right, so in our book, we talked about the fits and how they are considered. So here's the running and sliding fits, okay? So American National Standard running and sliding fits. And you can see there's a class RC1, class RC2, class RC3. Okay, so these are the class specifications of a type of fit. Sorry, having a little trouble here. So you can see the national size range in inches, so as it goes up, so if it's over 0.12 to 124, let's do the top one, 0 to 0.12, the clearance is 0.1. For a hole, you're allowed 2 thousandths greater, the shaft can be 1 thousandth smaller, okay? Want you to work through this, come to Dan or myself for any questions you might have on it. We are going to jump into geometric dimensioning and tolerances. Okay? We're just going to talk a little bit about this. You're going to learn more about this in the GD&T, or coordinate measure machine, quality assurance. I forget exactly which course you start into it again. The symbols show the tolerance as a form, profile, orientation. You can follow through in your book as well. These are your basic symbols. Okay? So datums are identified by the filled triangles labeled A, B, C, and D. D and E, sorry. Here I am on the back side. So as you can see, A on the bottom, B on the upper right hand corner, C in the middle to the left, D is up top here, and then E is this section as well. Okay? So real quick, let's break down this bottom. So this is section AA. This is a sectional view. As you can tell, because it's cross-section, it shows the interior holes within it. Just showing you dimensions. Okay? So what it's saying is your datum line here is the top surface. This is the finished surface. This is datum A. Alright? So we want to make sure this is very common in a machining operation. We'll come in and we'll face off the topping, the top, stock, rough scale, and so forth. We machine it down, and then we start measuring from there. Okay? This is going to be our through thickness piece. So this could be referred to as our Z dimension, or our Z axis. Alright? Now if we look over here to the right, it's got the triangle piece, and it's given us a 5 thousandths tolerance. So we know that means flatness. So that means the flatness has to be within 5 thousandths. Alright? So what does that mean? That means that as we come along a straight line, pretend it's straight, I'm going to make it very drastic, that it cannot vary more than 5 thousandths difference. It has to be within 5 thousandths of an inch flat, all right, on that top surface. All right, we'll go up to datum line B. All right, so datum line B is here on this corner section. All right. And what this is showing us, this is an object line. So as you can tell, this outside line here is this bottom section. What this is giving us, this isn't showing us a phantom line. This is not a phantom line. This is an outside dimension. This section here is showing the radius, but it's given us this dimension here, okay? So real quick, we've got a radius of 0.312 inches. So we know from here to here is 0.312 radii, all right? We have a perpendicularity of 5 thousandths of an inch to A. Okay, so what does that mean? A is our top surface, this is our bottom surface. So when we're looking at perpendicularity, we want to make sure that we are within 5,000ths of an inch of a squared triangle. So what does that mean? That means we have a theoretical right triangle, is that it can only be out, this distance can only be out 5,000ths of an inch from perpendicularity. Okay? That's to datum A. It's our primary one. Now, let's look at this thing right here. So here's our feature frame as well. So this is a profile condition. Profile of the surface now tells us it is 0.0220 to 0.016. All right. Over here again, perpendicularity of 0.005 to an A and a B. Now there's our C datum line as well. Okay. And then our D is on the outside edge. Sorry, our D is up here on the top, down here on the bottom. So we're going to have to start working through these fittings, or these portions as well. Okay. I want you to work through them. Any questions you have, come ask Dan or myself. Starting to break down into the feature frames. The feature frames is a lot of work to get used to. You will get better at them. I am not so focused on the feature frames per se in this class, because right now I believe that the best portion of it is just finding out, making sure that you can draw this part time and time again, consistent, reliable, and repeatable. And then we will start breaking down more of the G, D, and T symbols, feature frame controls. We're going to work a little bit on that still, but we're mainly focused on the outside, the main print dimension. Okay? So here it breaks down parts of a feature frame control. So the first component always contains one of the 14 geometric characteristic symbols. So in this case it is flatness. The 0.2 is the second compartment. Always contains the tolerance information, the tolerance value, modifiers that describe the tolerance conditions. So let's look at this one here. Okay, so the next one down below that. All right. So when we start talking about the difference within symbols, you can always turn to page 222. These are your G, D, and T symbols. So this is circular runout of 0.2 thousandths. Okay. The third, fourth, and fifth compartments, when used, always contain datum information. So as you can tell, you have your primary, your secondary, your tertiary. All right. Read through this section as well. Excuse me. So it gives you a dimension, but then the feature frame also, oops, sorry, wrong button. The feature frame tells you that it has to have flatness to a 0.2. So what it's showing you here is the surface plate, two parallel lines, they have to be 0.2 apart, just what we showed on my drawing earlier. Okay. So if we just had, real quick, so one of the things that this helps distinguish between is that it's 0.2 from this side to this side. And if we had a dimension of 0.4, it could be 0.4 this way, right? So we could have plus or minus 4 thousandths. We could have a total of 8. But that's not, so that's quite a bit. But then once we read the flatness symbol, we know that it has to be within 2 thousandths, or 0.2, okay, instead. So we're going to look at this. We're going to talk about location, the circular runout, total runout, circulatory feature, so forth. Okay? Cylindricity, moving forward on this. So what this one is showing us, top left-hand column, or top left-hand print, we're at 0.3. Okay? So that's our tolerance zone. Right hand is showing us it can be between 12.8 and 12.0 diameter-wise. The A, so this A portion right here is just a reference point, a line, showing us that it's 90 degrees from the center line out, so it also could be considered as part of a datum line. You can use a datum line that can be imaginary point anywhere here. A lot of times in cylindrical parts, your center point is always going to be one datum line. Okay? You're going to pull a lot of measurements off of your center line. You're always going to stay the center line of the point. A bed or fitting, a round portion, so forth, always in the center line. Okay? Then you can work your way out from there. So as you can tell on the top right hand column, it shows us that it can be 0.3. So you can see there in the middle, it's kind of cattywampus. It looks kind of like a caterpillar, right? But now if we come down over here, off of just showing us a tolerance of 0.3, now we've got the same dimensions, 12.8 to 12.0, but on our feature frame, now we have a cylindricity. Cylindricity, okay, which means that basically it's cylindrical. I'm having a hard time with that word today. Apologize. Now look at the difference. Is that it has to be squared, but it has to be straight along the edges. However, you're allowed a 0.3 tolerance, basically almost like a wall thickness is what you're allowed. Okay. Instead of being bowed, it's only allowed to be 0.3 difference cylindrical. All right. Figure 33.135, perpendicular feature. So what it's showing you here is it has to be perpendicular. So this is very similar. I showed you a minute ago. What you're on 0.04. What it's saying here is that it's showing there's a 0.04 thousandths wide tolerance zone of being within 90 degrees. Okay? You're only allowed within that small zone. So the feature frames are a way to convey a lot of information very fast if you know how to interpret your way around them as well. So here's your angularity, okay?